Hello, everybody. Today we're going to be talking about complicated relationships, and I mean the mathy kind between variables. If you were thinking this was something else, I suggest you find a different video. If you are interested in seeing how strange things can get when you're looking at multivariable functions, then I suggest you stick around. Let's imagine we have some function, let's call it w, and w is a function of two variables, x and y. We'll call them that for now. X and y could be parameterized in terms of some third variable, usually time, t, for example. So x is a function of t, and y is a function of t. We might ask ourselves then, how does w change with respect to that third variable, time? We can figure out how we've already done partial derivatives between w and x and w and y, but how do we really get through that intermediate x and y to figure out how w changes with t? Well, we have to employ the chain rule, which is for multivariable functions. Let's imagine we're going to increment along our function w. We want to see how we change. Well, we can step a little bit in the x direction, and w is going to change with respect to x. So we look at the partial derivative with respect to x, and then we multiply that by the little step we took in the x direction, delta x. We can do the exact same thing in the y direction. So now we're looking at a change with w with respect to y. Maybe it's steeper that way, and it's going to change more, multiplied by the little change we have in y. Well, we can kind of do some algebra tricks here. We're going to divide everything by delta t, a little change in that third variable. So we're going to get delta w over delta t equals partial with respect to x, delta t, plus partial with respect to y, delta y over delta t. Now we can do the calculus thing, and we can take the smallest step we can imagine. We're going to take the limit as x, delta y, and delta t all go to 0. And what that does is essentially it gives us the limiting step we can take, and it's going to turn all our deltas into d's. So dw dt is going to, or delta w delta t is going to turn into dw dt equals. Partial is going to stay the same as it was, partial with respect to x, and now we have the derivative of x with respect to t. It's an actual derivative here. See that the d's are straight up and down with their sticky part. In principle, x could depend on more than just t. It could be a partial in that sense. Since x only depends on t here, we can do the standard derivative. It's worth saying that I guess all 1D derivatives are technically partials in a trivial sense, so it doesn't really matter whether it's a curly D or a straight D. And then we do the same thing for the y direction. So what we have here is the total change in w with respect to t is equal to this little change in respect to x with dx dt. It's exactly what we'd expect with the chain rule if we had w depending on some function of x that also had some function of t inside of it. It's just that w depends on two things now, and to get the total change in w, we add the chain rule with respect to x and the chain rule with respect to y. So this is our chain rule formula for multivariable functions. We can visualize this with a really handy tool called a tree diagram. If you're looking at a complicated function where w depends on 2 or 3 things and each of those things depend on some other things, a tree diagram can really help you understand the relationships between all those variables and give you a visual way to interpret this formula. So for example, we have this nested relationship where w depends on x, which depends on t, and w also depends on y, which depends on t. So we can start drawing our diagram with w at the top. There's two possibilities for what w can depend on. W can depend on x. We draw another node there to represent x, and we go some other branch over here with the y. Well, y and x both depend on the third variable, t. So we draw its own little node down there. We label it t, and then we connect x and y to that. So now we've built this kind of diamond. This one doesn't look especially tree-like, but we call it a tree diagram anyway. Each of the connections between these points, w, x, y, z, there's no z, t, here, is the derivative. So if I go from w to x, that's the derivative of w with respect to x, the partial, and the same thing for the y. If I go from y to t, that's going to be dy dt and dx dt. So now, given this diagram, I have a problem that asks me to find dw dt. W, the thing on top, is where I start. And then the thing I'm taking the derivative with respect to, t, is where I end. Goal, it's my goal. What we want to do with this diagram is we want to start with our start, and we're going to take all possible paths between our start and our end. And then we're going to add everything we encountered together. So if I take this first path to the left, we're going to get dw dx is my first thing. And then I'm going to go down this next path, dx dt. I'm going to multiply that because it's on the same path, dx dt. Well, I finished that path, I got to my goal, but there was another way to get there. So I need to add that possibility to what I've started with, and I end up with dw y dy dt. And that is the complete way to calculate this derivative dw dt. If we do it with a specific example, let's say w is just the simple product between x and y, but x and y are parameterized to be a circle. That's a nice common one to do. So we'll have x as cosine of t and y is sine of t. So as they go on, these two alternate each other, and we basically build the unit circle. Well, I have this relationship, w is a function of x and y each is a function of t. I could just plug these in here and calculate the derivative with t, but we're going to find as the situations get stranger than this formula here with the tree diagram is a nicer way to go. So we have four derivatives to calculate. dw dx is just y. Remember, x is the variable, y is the constant out front, and so we just sift out that constant. Likewise, dw dy will get us x. Now we have to do the t derivatives. dx dt is the derivative of cosine, which is going to be negative sine t, and dy dt is the derivative of sine, which we should hopefully know is cosine. So now we've got our four factors here. Now we need to put them together according to the formula. So we're going to get dw dx and dx dt. We multiply those together, and we get negative y sine t plus x times cosine t. And that's about as far as we can go there. Maybe they'll ask you to evaluate it at t equals pi over 2 or something like that. Well, now what we can do is we have this in terms of y and x. We usually want to get this just in terms of t. So we take our definitions of x and y and plug those in. So we'll get negative sine squared t plus cosine squared t. We're going to evaluate that at t equals pi over 2. Cosine goes to 0 there. Sine goes to 1, we square it, the minus sign multiplies out in front, and so we get negative 1 as the derivative of w with respect to t after all of that. So the tree diagram helps us to very efficiently build what this derivative is going to look like. Why stop at 2 variables? We've done 2, we might as well do 3. We'll get w as a function of x, y, and z now. And all of these x, y, and z depend on t. So we can define a function, for example, w equals x times y plus z, really switching it up here. And then we're going to have the same definitions we had before. Cosine t, y sine t, and then z is just going to be t itself. We want to evaluate the derivative dw dt at t equals 0. So dw dt at t equals 0. And the first thing we should do is we should build the tree. We still have a starting point, w. We still have an ending point, t. It's just now that we have a third variable that depends on t, we have another path to include. So we still have an x. I'm going to push y into the middle here, and then z is over there. So we have a path connecting w to x to t, w to y to t, and w to z to t. Same thing. The paths connecting the nodes are the derivatives. So what we're going to do is we're just going to basically write out the formula. It's going to look like what we've done already. It's just now this z path gives us a plus dw dz plus, times dz dt. So now we're just adding more terms, which is pretty easy. We like that. dw dy, dy dt, plus dw dz, twist, dz dt. We've already calculated the derivatives of w, y, and t. We can add to the mix dw dz, which is just 1. X and y are constants with respect to z, so that whole term goes away, and we're left with 1. And then, hey, look, dz dw is also going to be 1. Sorry, dz dt. I apologize. 1. So not a whole lot of excitement there. We take the expression we already found, our negative sine squared t plus cosine squared t plus 1. If we evaluate this at 0, well, now the sine part goes to 0. The cosine squared part becomes 1. We add that to the 1 we get from the z dependence, and well, now we get 2 as our derivative. So we can easily adapt the formula if we have more variables by just adding an extra path. Well, what if x, y, and z all depend on 2 variables? What do we do in that situation? Well, what we can do is we essentially just get more choices. If we start at w, here's x, here's y, here's z. And now we're going to say that x depends on 2 variables itself, r and s, and y and z do the same. R and S are just kind of generic dummy variable names here. A good example of x, y, and z depending on multiple things could be like polar or cylindrical coordinates, where each one of those could depend on a radius and an angle. Here, we're just generic R and S. They could be anything we want them to be. R and S. So all of these functions have a path that leads to R, and all of them also have a path that leads to S. We get these cool, like, star crossing path diagrams. You could also just drawing the bottom half here, X could go to R and S, Y goes to R and S. They're all the same R and S, but maybe it's a little cleaner. If you like that, you can draw your diagrams like this, where each variable branches to its own things, and you can just trace the paths. Tree diagram works the same. We start at W, we go to X. If our end goal is R, we're going to take the path that leads to R, and we could ignore the S path altogether. The relationship between X and S is still there, but if we don't really care how W changes with respect to S, we're not going to include that path in our derivative. So we can write dW dr. This time I am doing a partial because W depends on multiple end goals now. And we look at all the paths from W to R. We go from W to X to R, W to Y to R, WZ to R. And we add out those possibilities. So we get dW dr, or sorry, x dx dr plus dw dy dy dr plus dw dz dz dr. And if I want to find dw dr ds, bleh, you write the exact same formula I just wrote, but you replace all the r's with s's. It's that simple. So it's just really which one you use is going to depend on what you're interested in for W. If you want to know how specifically W changes with S, you're going to use the formula I'm currently wasting time writing right now. dz ds. Ta-da! So this is when we have multiple nested variables. W goes to x, y, and z, which each all go to r and s. You could have situations where x and y depend on r and s, and z only depends on s. So you wouldn't have this branch here, and you would just kind of stop. You wouldn't have a path from w to z to r. So you would only include the paths that actually lead you to where you want to go. We can do a quick example to show how this works. We have w equals x plus 2y plus z squared. And we're going to define x as the ratio of r and s. We're going to define y as r squared plus the natural log of s. And then z is going to be 2 times r. So if we were to build this diagram, W does connect X, Y, and Z. Both X and Y go to R, and then Z also goes to R, but only X and Y go to this other variable, S. I want to find the derivative dw dr. So I look at my start, W, I look at my end goal, R, and I consider all the paths that get me there. So X, Y, and Z all have paths that get me to R, so I need to carefully take those derivatives. We will write them down here. dw dx is just 1. dw dy is 2, and then dw dz is 2z. dx dr. Now we go over here and we look at this relationship here, and we get 1 over s. R is the variable, 1 over s is the constant. dy dr, just that first term matters here. We get 2r. And then finally, dz dr, we get just the constant 2. We put it together, and we have the x things multiply together, so we get 1 over s plus the y things multiply together, 4r plus 4z. And z in terms of r is, so I guess I'll just write 4z, which is equal to 4 times 2r, or 8r. So this is equal to 1 over s plus 12r. If we were asked to find the relationship with respect to s, well, now we have to look at those s derivatives. So dx ds, that's a mouthful to say, is going to be negative r over s squared. dy ds is 1 over s, just a derivative of natural log. And then dz ds is 0. So I don't have to consider any paths involving z. We just do the 2 with x and y. So now we're going to use the first and last column here, w, and then the s ones. So dw ds is equal to negative r over s squared plus 2 over s. And there you have it. two completely different derivatives of w based on what your end goal is. It's going to change differently in one variable to the next. The last thing we want to talk about regarding this topic of the chain rule is what happens when some of your variables are constrained. In other words, especially in physics or science, where you're looking at the relationship between many things, you can have, w as a function of x and y, and then, x and y are all constrained to behave a certain way by some other relationship. A really common example would be like in thermodynamics. You're looking at U, which is the internal energy of a system. It's usually some strange function of pressure and volume and temperature and things like that. Well, if you're working with a gas, well, then those variables are constrained by a little friend called the ideal gas law, where PV is equal to some set of constants times T. They have to behave this way regardless of how they're arranged in terms of U. And so when you have these constraints, you have to think about really what relationships are going on. What depends on what becomes very important. So to kind of illustrate this, it's best to just kind of do an example. And so we're going to have w equal the sum of the squares of our three variables, x, y, and z. This function kind of represents the square of the distance from the origin, maybe. But maybe we're only interested in points, so certain points. So we put on a constraint that we only want z to be equal to x squared plus y squared. We have z kind of confined to this paraboloid in space. Z only on paraboloid, defined by x squared plus y squared. The values of the derivatives of w are going to depend on what we're labeling as dependent or independent. Or often, in certain times, especially in like thermodynamics here, you might look at a certain process where pressure is held constant, but V and temperature, the volume and the temperature are free to change with respect to each other under that constant pressure. And so pressure would be kind of like independent here. It's not really doing anything. It's not changing, and so how it changes with respect to U would be different than if pressure were changing. So we're going to make a couple different choices. We're going to suppose that W depends on all these things. W depends on X, Y, and Z, but we're going to leave X is independent. So we can look at how different choices will affect the derivative. So we could have one choice where W and Z are dependent, or a different choice where W and Y are dependent. X by definition is always going to be independent here. And so if Z is dependent, that leaves Y as an independent variable. And if Y is dependent, that leaves Z as an independent variable. So we're going to look at this first choice here, where we have Z dependent. Z dependent. That means that Z will depend on both of our independent variables, X and Y. When we write our function, we want to eliminate Z from this. Z is dependent on X and Y, so when we take derivatives of W with respect to X and Y, we want to make sure that the Z is taken care of. So X squared plus Y squared equals, by our definition up there, Z is X squared plus Y squared, quantity squared. If we factor this all out, we get x squared plus y squared equals x to the fourth plus 2x squared y squared, those are our cross terms, plus y to the fourth. So now we have w rewritten in terms of only x and y based off the constraint impose on our dependent variable z. So if we want to find the derivative dw dx, well, now we're just taking the partial with respect to this expression here. Anything that is y is treated as constant, and so what we'll get is 2x plus 4x cubed plus 4xy squared, and that's where we end because the y to the fourth is a constant. This means we can solve for y squared, which will get us z minus x squared. So now we can plug this into our expression for w. We get x squared plus y squared is z minus x squared plus z squared. Well, this is kind of interesting because the x actually just straight up cancels out. X squared minus x squared, and we're left with w as equal to z plus z squared. If we take the derivative with respect to x, it's just 0 in this case. So we went from under one definition of what's being held constant or what's independent versus independent is actually w changing with respect to x. In the previous example where we had z as the dependent variable, dw dx was 2x plus 4x cubed plus 4xy squared. That's what we found. Under this different set of assumptions, w is constant in x. So it's really important that we need to look at how all these relationships kind of fit together to give us the overall nature of our function under this constraint. We can look at another example. We're still going to have w be this square of the distance from the origin. All of our things added together squared, but we're going to have a stranger looking constraint where now we have z cubed minus xy plus yz plus y cubed, because why not, equals 1. It's a much more complicated looking constraint. Here, if I want to, make something z dependent, it's actually much more difficult to solve for z or y under this thing. And so this is where our derivatives, our chain rule becomes more useful in this case. So we want to find the derivative of dw dx at the point 2, -1, 1. We're going to say that both x and y are independent. So if I take dw dx, I'm going to get 2x plus 2. Y is independent, so that whole term goes to 0. But z, x depends on z in this case. So we will have 2z dz dx, which we can now take the same x derivative of our constraint to help us figure out what this dz dx looks like. So we'll get 3z squared dz dx minus y plus y dz dx. Here, just as a reminder, y is a constant in terms of x. Z just becomes the derivative of z with respect to x, and then the y cubed is constant. So this is equal to 0. We can now take this expression here and solve for dz dx. We can move that y over to the other side. Dz dx multiplies both of those terms, so we can factor out a 3z squared plus y equals y on the other side. And then we divide through to get that the dz dx derivative is equal to y over 3z squared plus y. So through taking our constraint and deriving it implicitly, we were able to get an expression for dz dx in terms of y and z, which we can now take over here back to our original derivative of w and plug that in. So dw dx equals 2x plus 2zy over 3z squared plus y. We've got everything in terms of y and z and x, and so we can just plug in our point, 2, -1, 1. So we'll get 4 plus z times y is -1, so -2 over 3 times 1 minus 1 is 2. So we get 4 minus 1 is 3 at the end of all of that. There's a notation that is very common when looking at dependent or independent variables. So when we did this, we did dw dx, and we kept y constant. This notation is actually very common if you take an upper level thermodynamics class, which is all partial derivatives all the time. You'll use this notation to say, hey, I'm taking the derivative of w with respect to x, and I'm leaving y constant. And that's what we did here. Because y was independent, we essentially treated it like it was constant in terms of x. Z, anything that's not a subscript here, gets derived normally or implicitly with respect to x. So this just means subscript is independent, and that means you treat as a constant. Anything that is not subscripted here, z in the example we just did, should be assumed to be dependent on x. You have to figure out what that derivative might be. All right, we've tangled that web, we've climbed the tree, and now we hopefully are masters of the chain rule for multivariable functions. Thanks a lot. Whoa.